Good evening. My name is Isabella Gladden, and I'm a junior in the Randall Research Scholars Program majoring in mechanical engineering. This semester, I worked on a project looking at starch inclusion complexes with fatty acids that had a chain length of 18 with Dr. Kong in the Department of Human Nutrition. So first, I would like to talk some background about the structure of starch itself. So starch is a polysaccharide that is composed of amylopectin as well as amylose. The ratio between these two in starch depends on its botanical source. As you can see from the image, amylopectin has a branch structure with some linear side chains, while amylose is composed of one linear chain that then forms a helix. Using this structure, we are able to form starch inclusion complexes. So as you can see, a guest molecule that has a hydrophobic chain is encased within the hydrophobic interior of an amylose helix. We use amylose as our structure as it is able to better wrap around the guest molecule, thus forming better inclusion complexes. In this research, we use fatty acids as our guest molecule, as fatty acids are molecules with a carboxyl head with a hydrophobic tail. In this case, all of the tail lengths were 18 carbons. Fatty acids can be either saturated, which means that they have no double bonds in their chain, or unsaturated, meaning they have one or more double bonds in their chain. Previously in our lab, we looked at the effect that chain length of the guest molecule had on thermostability. In order to do this, we used alkyl galates, which are the following, and obtained the following results. We found a differential scattering calorimetry graph, an X-ray diffraction graph, as well as Fourier transform infrared spectroscopy. From the DSC graph, we found that as chain length increased, so did the thermostability, as it took a higher temperature in order to dissociate the complex. Additionally, from our X-ray diffraction graph, we found that the longer the chain length, the better inclusion complexes were formed due to the characteristic peaks that we observed on the X-ray diffraction. In this study, we used fatty acids with chain length of 18 as our guest molecules. These included stearic acid, oleic acid, elatic acid, linoleic acid, alpha-linolenic acid, as well as conjugated linoleic acid. First, stearic acid is a saturated fatty acid as it does not have any double bonds. Therefore, its three-dimensional structure is very linear. Oleic acid is a monounsaturated fatty acid since it has one double bond, shown here. Since the double bond is in the cis form, its structure changes to this in the three-dimensional structure. Elatic acid also has a double bond in the same location as oleic acid, however, it is in the trans form, so its structure is less affected in three-dimensionally. We also use linoleic acid, which has two double bonds, making it a polyunsaturated fatty acids. These double bonds change the structure by also giving it a slight curve in the structure. We also use alpha-linolenic acid, which has three double bonds, and this greatly changes the structure as it has a larger curve than the previous guess. Finally, we also used conjugated linoleic acid, which is a family of isomers of linoleic acid. So depending on the structure, whether the double bonds are in the cis or transformation, the three-dimensional structure can vary. In order to form our inclusion complexes, we are mainly focusing on three methods. The first is the dimethyl sulfoxide method. So first, starch is dissolved in dimethyl sulfoxide as well as heated. At the same time, the guest molecule is also prepared in the same way. This preparation of the starch leads to amylose forming random or loose coils, and then we add the guest compound and then quench it with water and allow it to slowly crystallize into an inclusion complex overnight. The next method we are using is the alkali method, which is similar to the DMSO method. However, the starch is first dissolved in potassium hydroxide and then heated. The guest is also prepared in the same way, and this treatment of the starch leads to the similar result of the loose helices. The two are then combined and hydrochloric acid is added in order to obtain the desired pH. The sample is then allowed to form the inclusion complex. Finally, the last method we are using is the empty helix method. So in this method, starch is either dissolved in water and heated to about 140 degrees Celsius, or dissolved in DMSO and then heated. And then ethanol is added to the samples before the starch is once again washed with ethanol and dried. So in this case, preformed helixes are formed before the guest compound is added with a solvent in order to form the inclusion complex. These inclusion complexes have many applications, one of which is the preservation of the guest. So when the inclusion complexes are formed, they are able to better withstand temperature as well as solubility, and this is preferred for increasing shelf life of certain gas molecules which might be sensitive to high temperatures or water soluble. Additionally, starch inclusion complexes alter the digestive behavior as they are more resistant to digestion. Shown on the right is a graph that we obtained from our previous research, where it shows that the increase in the chain length actually led to an increased amount of slowly digestible starch. So this altered digestion behavior has many health effects, as it could be used to possibly treat diabetes. Instead of consuming starch normally and the body being able to really quickly digest the starch into glucose and have a increase in the blood sugar, starch inclusion complexes take a longer time to digest, which means that there is a more steady increase in the blood sugar. Additionally, starch inclusion complexes can be used as a delivery system since they are able to withstand digestion up until the small intestine. So certain guests can be enclosed and delivered to a certain part of the digestive tract. In the future, in our lab, we would like to continue to form the inclusion complexes, as well as complete an analysis of the samples similarly to our previous research, using X-ray diffraction, differential scanning calorimetry, and Fourier transform infrared spectroscopy. If there are any remaining samples, we would also like to do an in vitro digestion study, as this can also give us more information about how well the inclusion complexes were formed, as well as how resistant they are to digestion. And once we have completed all of our characterizations of the results, we would also like to analyze and draw conclusions from these results. With that, I'd like to open up for any questions.
Yeah, on the previous slide, you mentioned that you were going to continue the analysis of your samples. What are some other facets that you're going to continue in that analysis?
By analysis, I meant that we were going to observe our results from the various characterization techniques I described, and then draw our conclusions from what we found. So our characterizations of the results include the X-ray diffraction graph to show whether or not we were able to form the inclusion complexes, as well as the Fourier infrared spectroscopy. And then additionally, the differential scanning calorimetry will tell us how thermally stable the inclusion complexes are.
As a characteristic, how do you determine the thermal stability of the inclusion complex?
So I believe it was slide 3. So the stability, as shown on the slide from our previous results, essentially with the differential scanning calorimetry, you look at how high the temperature has to go in order for the inclusion complex to dissociate and break apart into the guest and the starch. So what we saw previously was the longer chain length led to a higher thermal stability. And we're going to see which of the 18 carbon chain length fatty acids is best able to withstand that temperature.
And then we have an online question. What forces are involved in the formation of the inclusion complexes?
So there's two main things. So between the starch itself and the molecules, there are intermolecular forces that are involved. However, as I mentioned before, the actual tail of the fatty acid is hydrophobic, and the inner part of the amylose helix is also hydrophobic. So a lot of research has been dedicated to further confirming that it's this hydrophobic interaction, mainly that helps to stabilize the gas within the helical cavity.
Any other questions from our online guests? Very good, Leila. Thank you for your wonderful job in presenting your research. Thank you.